Good afternoon, everybody. It's an honor to be here today and share with you some of the work that we've been doing in my laboratory. We've spun this out into a startup known as Ingel Therapeutics. It's the latest stem cell product that we've developed in my laboratory, and we're very excited by the prospects for restoring vision in retinitis pigmentosa. So indeed, our mission is to use our innovative cell therapy to bring light back to our patients. Ingel Therapeutics is a platform company with two main bits. We have a cell development platform in which we're able to isolate retinal neurons, rods, cones, and retinal ganglion cells in high purity and viability. That's been a very difficult prospect for cell sorting. We can purify these cells up to 95% with very high viability, and that's new. Our biomaterials platform is a hydrogel that we think is also a platform that we can use for delivering cells intravitreally, subretinally, and indeed to any compartment of the body. So again, we can purify retinal neurons with high purity and viability from fetal sources, embryonic stem cell sources, and iPS cell-derived sources. We've identified rods, cones, retinal ganglion cells, and RPE cells. And once we can isolate and purify these cells, we can expand them greatly in culture, generating trillions and trillions of cells for banking and for clinical use. So again, two parts to this therapy: the cells and the hydrogel. So the hydrogel is natural biomimetic, composed of components of the vitreous, and we can functionalize and modify this with in situ cross-linking to modify the stiffness and viscosity, tailor the degradation time, and we can encapsulate a variety of biologicals. And therapeutics, growth factors, antibodies, small molecules. What I'm focusing on today are stem cells, or in fact, retinal precursor cells. So these are rod cells that can be expanded greatly in culture and make only rods. And that's something we've developed in my laboratory using low oxygen tissue culture techniques. So the benefits of this is it's injectable. So it's less invasive, and it alleviates the shear stress inherent in what's being done in the clinic now, which is injecting stem cells in buffer. And when you do that, you kill almost 70 or 80% of them. We've published that data. So we prefer to inject live cells. We think that's a much better approach. We can target these cells. We can deliver them where we want them to be in the retina. They adhere to the ILM if we tailor it to that purpose. So we get them to the retinal surface where we want them to be. And they evade the immune system. And we can show that with this data here, showing a lower immune activation following injection. In black, we see what happens when they're injected in buffer. They get attacked and they die. If we inject them in the colored bars with various formulations of our hydrogel, they are not attacked and they survive. Important with the hydrogel injected into the eye, specifically into the vitreous, it's going to degrade. We don't want it to clog up the trabecular meshwork and elevate IOP. That's been a problem for a number of hydrogels experimentally and clinically. So we get an elevated IOP. Initially, of course, when you inject something into the vitreous, it goes down right away and it stays down following degradation. So what are we targeting? Retinitis pigmentosa neuroprotection. Okay, so we're targeting the early stage at the end, the mid stage and the early, let's call it the early late stage and the late early stage. So a broad spectrum of retinitis pigmentosa where photoreceptors remain but are injured. And when I say we want to restore vision, we have some good evidence that we can actually make photoreceptors that are alive work better. Some of the molecules that we're secreting from these cells actually increase outer segment formation and make these rods work better, thereby improving vision. So we believe that one factor is not enough, and neuroprotection over the years has shown that with a lot of failed one-factor approaches. So our cell delivery system delivers at least 350 molecules that we've extensively characterized, and they attack 4 different pathways: neuroglycolysis, metabolic stress, oxidative stress, and neuroinflammation. All of these lead to cone death. So if I didn't emphasize this enough, we're trying to save the cones. That's the most important thing for RP patients, is to preserve central vision and preserve the cones. So these cartoons really highlight our approach. So we inject this hydrogel containing these retinal precursor cells into the vitreous, where they take up residence at the base of the ILM and secrete their neuroprotective factors. So in blue in the middle panel, you see our hydrogel with its components. In red, you see the cells. These are rod precursor cells, post-mitotic, that can secrete, again, these molecules. in two different flavors, exosomes and microvesicles. And they, again, are really dealing with four large processes: cell processing, retinal neuroprotection, retinal development, and neuroprotection. So this cartoon really highlights what I'm talking about. We have the cells secreting these microRNAs, growth factors, a variety of factors being secreted through microvesicle or exosome transport, and we've characterized them extensively. So I think that lets us stand apart from a variety of exosome startups in the CNS space. We know what these cells are making. We believe that pure cells lead to pure exosomes. And so we've extensively characterized 350 molecules that these cells are secreting. They break down largely into four groups, again, attacking neuroglycolysis, metabolic stress, oxidative stress, and neuroinflammation. Again, the lesson that I've learned over the years is that it takes a broad approach to save cells. So this is the most important slide to me. I'm a neurobiologist, a retinal development expert from many years of training, if I must say, working on the RD1 mouse for 30 years. I've never seen anything that can do this type of neuroprotection. So the RD1 has a rod defect, but the cones die rapidly following it. So there's a lot of extensive data has been published on this RD1 mouse. And dare I say, a lot of data has not been published on the RD1 mouse because most things don't work to save these cones. And so if you look at the, let me go back. If you look at the panel on the left in the center, you see the central retina at day 50. All the cones are gone. And if we deliver these cells, you see some cones can remain. These cells are neuroprotective. But again, if they're delivered in the hydrogel, we see a 10-fold increase in these cone survivals in the central retina. 3-fold increase in cone survival in the peripheral retina at 50 days of age. Very little is published on this animal at 50 days of age because almost all cones are dead in almost every study that's been published. So that's our approach. We want to save cones in the retina. We have a great team that can do that. Our CEO, Pierre Drummel, our Chief Science Officer, Dipti Singh, we have expertise in polymer science and cell culture and cell isolation. Patrick Zhang, our co-founder, business officer, is here today. He's an expert in business development. He's done it. We think we have a great team. We have Dean Elliott, who's our close clinical advisor. Myron Spector helped develop these hydrogels. He has 50 years of experience in that. We know how to tailor these hydrogels for our purpose. And Connie Stepko has joined our team. Connie, I dare say, is the smartest retina person in retinal development. She's at Harvard Medical School, Howard Hughes investigator, and we're very happy that she's going to lend her brain to developing this therapy. Thanks very much.